This observation shows relatively bright mounds scattered throughout darker and diverse surfaces in Chryse Planitia. These mounds are hundreds of meters in size. The largest of the mounds shows a central pit similar to the collapsed craters found at the summit of some volcanoes on Earth. The origins of these pitted mounds are uncertain. They could be the result of interaction of lava and water, or perhaps formed from the eruption of hot mud originating from beneath the surface. These features are very interesting to scientists who study Mars, especially to those involved in the ExoMars Trace gas orbiter mission. If these mounds are indeed mud-related, they may be one of the long sought-after sources for transient methane on Mars. Although not as pronounced as on Earth, clouds are common features on Mars. The Martian atmosphere has limited water vapor, however the temperature and pressure is such that the atmosphere is usually close to saturation and produces clouds. While cloud gazing one day, Curiosity rover saw a sequence of straight parallel rows of clouds, all flowing in the same direction. These are gravity wave clouds. Similar to the waves that follow a pebble tossed into a pond, gravity waves are the result of gravity trying to restore them to their natural equilibrium, which causes a ripple in the atmosphere that is then seen in the clouds. Such waves are common at the edge of the Martian ice caps but thought to be less frequent over its equator. Dust devils on Mars form under the same conditions as in Earth's deserts. These rotating columns of air pick up dust and debris typically on clear summer days when the ground is very hot. These form when there is a contrast in heating among surrounding objects. The hotter part of the ground hits the air above it. The air is hotter than the surrounding air, so rises, punching through the cooler air above and creating a vertical column of warm, rising air. On Earth, dust devils are pretty small, ranging in height from 10 to 100 feet. On Mars, however, dust devils several miles tall and more than 100 feet wide have been recorded. Since they are more aggressive, dust devils on Mars are thought to play an important role in the planet's climate. These transport vast amounts of fine particles of dust from the surface to the upper atmosphere. The dust alters the reflectiveness, thereby directly influencing the temperature on the surface of Mars. This image shows a cylinder of rock the size of a piece of classroom chalk inside the drill of Perseverance Mars rover. The sample was taken from a rock on the rim of the Zero crater, and each core the rover takes is about 13 mm in diameter and 60 mm long. Data from the rover's instruments indicates that the rock is made almost entirely of serpentine minerals, which form when large amounts of water react with iron and magnesium-bearing minerals in igneous rocks. During this process called serpentinization, the rock's original structure and mineralogy change, often causing it to expand and fracture. Byproducts of the process sometimes include hydrogen gas, which can lead to the generation of methane in the presence of carbon dioxide. On Earth, such rocks can support microbial communities. This intriguing surface texture is the result of rock interacting with water as observed by NASA's Mars Reconnaissance Orbiter. The rock was then eroded and later exposed to the surface. The pinkish, almost dragon-like scaled texture represents Martian bedrock that has specifically altered into a clay-bearing rock. The nature of the water responsible for the alteration and how it interacted with the rock to form the clay remains poorly understood. Not surprisingly, the study of such altered rocks on Mars is an area of active investigation by the Mars science community. Understanding such interactions and how they happened helps scientists to understand the past climate on Mars and if the red planet ever harbored life. Recent studies indicate that the early Martian climate may not have been as warm, wet, and Earth-like as previously suggested. This is not a problem for finding life on Mars as one might think. Ongoing studies of dry and cold environments on Earth shows that life finds ways to adapt to such extremes. Such work provides hope for finding evidence for life on other planets like Mars someday.